So we start by recalling what happened yesterday, just very briefly. Basically, yesterday we covered this lemma 412, which the statement itself is also very clean. We have on the same vertex sets two graphs. One is the random graph G with linearly number of edges. This will be the sprinkling we want to do on top of the other graph H0, which we call which we assume it to be an expander with expansion rate 2, constant expansion 2 for all sets up to size n/5 small sets. And as a conclusion, we know that if you sprinkle G on top of H0, this expander, we can make it Hamiltonian. But note that we don't really get Hamiltonian with respect to the whole vertex graph. It could be that H0 does not span all the vertices, okay? So, and the proof of this, I would also like to just quickly recall through a very quick picture. Basically, it consists of two steps. The first step is by saying we make use of the H0, because H0 is expander, so you can do this rotation, okay, to get many of this pair of endpoints, different endpoints, red one and blue one. I'm a little bit vague now, but then we will get quadratic number of choices of this thing. Then since now we have quadratic many pairs, adding each one of which boosters, we can increase the length of the longest path. Then when you do this sprinkling in rounds, linearly in n number of rounds, each round constant number of edges, you can add n boosters to make it Hamiltonian. Okay, this is the big picture. So today we will go through yet another technical, maybe perhaps most technical lemma in this section. But before mentioning that, I want to say what we will see after, right? We need to get some motivation. Basically, using lemma 412 plus what we will cover now, which is this technical lemma. The proof itself is not long, but it's a little bit dry. So I want to add some explanation, which make it a little bit long. So this is 414, which says basically, if we have like a pseudo random graph, then we can find G minus W, which is a 2n/5 expander. We can find a large expander basically, where W is small. Okay, so just very hand-wavingly, why these two, they works quite well together, because now what we're gonna do is that we have our random graph at hand. We're gonna just separate a little bit out. That will be the G in lemma 412, which we do sprinkling afterwards. For the remaining part, we know that it's random graph, so definitely it's pseudo-random. Then we can apply 414 to find within a relatively large, by removing a very tiny proportion of vertices, a large expander. Now you sprinkle G, whatever we separated from in 412, we separated before, you sprinkle on top to make this very large, almost spanning expander to be Hamiltonian there. So then we get a very, very long cycle, for example. Hamiltonian with respect to the expander, right? Does it make sense? So I will make the lemma 414 precise, but let me just say the consequence of these two. So 412 plus 414, we have two very interesting consequences. These two will imply two results we will see. The first one is theorem 415, which again come back to our problem of finding long path of cycles in G and CO over N. So in theorem Okay, let me just write it down. This is already almost best possible. Okay, let me just quickly recall that before we have 1 minus log C over C. Remember the error term. Then we improve to 1 minus 1 over C up to some constant here related to the 1 over C factor. Okay, so all this improvement is still polynomial in the reciprocal of C, but now we have exponential decay with respect to C. So this is a big improvement. And we should see next week that this is basically best possible. Okay, and before this is theorem 4.5, right? You find only a path of this length. Now we can even find the cycle of this length. So this is 4.15, first consequence. Second one is, as I said, this is proved first by Bolobash, and then independently by Komlos and Samaradi in the 80s, the very sharp threshold of Hamiltonicity. So this is theorem 416. So if I let P to be log n plus log n plus some function that grows to infinity with respect to n. So it could be like iterative log or just any function grows to infinity with n over n. And GMP almost surely is Hamiltonian. Okay, so this bound is the sharpest possible. The only result even stronger than this is the heating time result, which says whenever you have minimum degree reaching 2, then you are Hamiltonian. But we will not cover that in these lectures. We will talk about this one. Okay, and just a very quick remark that you might also know, if I let this term here, if I change this plus to minus, then almost surely there would be a vertex of degree at most 1. So this is also the same threshold for minimum degree at least 2. So minimum degree at least 2, having vertex of degree at most 1 is the obstruction to Hamiltonicity. The implication to these two results is very short and easy. We will do it afterwards. So just know that we can obtain these two. So all we need to do now is to state 414 more precisely and to give a proof. That's today's goal. Then if there's time, I will say the implication. This is how you prove it, very short. Otherwise, we mention next week. Any question for the recap and the plan for today? Okay, so 414, let's get to this lemma. So if you recall, actually, we've done this before already a couple of days ago. So let me remind you that in exercise, if you recall, in exercise 4.6 and claim 4.8, there, basically, I'll write it down what's going on. We have in GNC over N, in this random graph with linearly number of edges, we can make it into a 2n/5 expander by removing W of size at most m, where the m there is something like this, linear in n with the coefficient reciprocals c. C is sufficiently large. Remember we have this. I think this is claim 4.2, which I leave as exercise. And the proof is very simple there. It's basically one paragraph proof. If you thought about it, you basically take a W that's poorly expanding, which is maximal in some sense. Then you say that removing that, the remaining is 2n/5 expander. That's it. So this is a short proof, but give you the drawback is that this error term, n/c, is rather large. This is why we have 1/c here, right? Now we need to do it more efficiently, like something dk exponential in c. So this is what we're going to do. We want now W smaller. Okay? A more economic way to do so. So as usual, instead of directly working on random graph, we prefer to work on pseudo-random graph. Because if we say that we grab some property and this property will be deterministic, so we can apply it to a fixed graph rather than random graph. And when you apply to random graph, you can just say, okay, with high probability, random graph satisfy this set of deterministic pseudo-random properties. So we would, again, working pseudo-random graph, the deterministic setting, essentially, lemma 14, which I haven't stated yet, but let me tell you basically where the expansion come from. We can remove a small set. What kind of pseudo-random property we're looking for, basically, to guarantee a large expanding graph. Follows from the following pseudo-random property. The first property is that there are few vertices of small degree. You can just do some few vertices of small degree. Okay, because usually vertices, their degree is concentrated around their mean. And small degree vertices, they are pairwise not so close to each other. They are far apart. Since there are very few of them, it's unlikely that they are close to each other. In our proof, actually, distance at least 5 will be enough. But let me just do like that. And the second property is that we have pseudo-random property, we have seen it before, is large set expansion, which says that when you have a set of size relatively large, then its external neighborhood reach, say, 80% of the vertices, 4n/5 or something like that. Okay. And the very last one, it's called upper uniformity. If you've seen sparse regularity lemma, this will look familiar to you. Basically, it says that there's no dense patch in the graph. I will make it precise, meaning that if you look at your graph, then you cannot find somewhere a patch, a subgraph, such that it's particularly dense here. That's impossible, which is kind of expected also in random graph, because random graph, the edges are distributed kind of uniformly. So it's unlikely that somewhere will be particularly dense. In particular, I want to mention that in lemma 4.14, which I will state it precisely, these three pseudo-random properties correspond to the condition 1, 2, 3, respectively. Okay, I'll make it rigorous. But even to state Let me see what order I want to do this. Do I, what order I want to do this? Yeah, okay, maybe I'll postpone the showing you the precise definition, the precise statement of 414, but give you the intuition first. Then this will motivate the statement of 414. But just keep in mind that 414 looks something like this. We have these three conditions. Then as a conclusion, we find a large 2n/5 expander. Okay, these three. So let's look at some heuristics or some intuition. How we can go about finding large expander. So basically we want to guarantee that all sets of size up to n/5, they expand by a factor of 2. We need to guarantee 2 expansion for small sets. So let's do that. The heuristic is that the first of the heuristic is that why is it like this? I choose this one. Okay, good. The first is that what we want. We want every set they expand by a factor of 2, the external neighborhood, right? Twice as large. This is x. We want 2x size here. So if a vertex, they have degree 1, this is dangerous. We already fail because this singleton guy, he only expand by 1. Okay, so the first intuition is that we need to be careful about small degree vertices. So intuitively, small degree vertices expand poorly. Okay, it's more likely that they fail to expand. So then that means it makes sense that when we want to prove some set expand, we're gonna consider them separately. Okay, say for u in v of g, we want to show that n of u expand. Okay, we want to show u expand. Now it makes sense to define u. So let me call S the set of small degree vertices without defining explicitly what I mean small degree, just some bound. When you fall below this bound, your degree, you are small degree vertices. Then I define U1 to be U intersecting S, the small degree vertices in U, and the remaining I call it U2. Okay. So we have to separate these two. So here maybe it's a picture. We have U1 and we have U2. They are disjoint. These ones are low degree, small degree. Okay. So we have to be careful about U1. But just by inclusion exclusion, what do we have? We have that we need to bound this guy, right? U1 unit U2 is U. So what we want to do is we want to bound this by inclusion exclusion. This is at least the external neighborhood of U1. But we have to be a little bit careful because U1, the neighborhood, it could look like this. So it could intersect U2. We want the external neighborhood of U1 unit U2, so we have to kick out U2. So just to be safe, or maybe it's good to keep this picture, right? Yeah, let me keep this picture. Right, we have U1 here. So minus U2, this is overkill, right? So we get the contribution from U1. Then we get the contribution from U2. Well, how I'm going to write it is the external neighborhood of U2 not in S, not in a small set of vertices. Then this is definitely disjoint from U1. We don't need to minus U1 anymore because U1 is a subset of S. U1 is the intersection with the small degree vertices. Okay. So here we have also this neighborhood. So this is the blue and red. All right. Then we have to kick out their intersection, inclusion and exclusion, right? Minus which is, oh, I didn't draw the intersection here. Maybe yes. Let me do kind of. Which color? Purple? No. Yellow? Let's do yellow. Here. They have some intersection, okay? Like that. All right. So basically, what I want to convince you that this is not hard to bound. Okay, it's large intuitively, the blue part. Why? Because U2 is a set of large degree vertices. So that means it sends lots of edges to the blue blob. And since our graph is upper uniform, there's no dense patch, right? If the blue blob is small, together with U2 is small. It contains too many edges, it's too dense. So this part is okay from upper uniformity. Does it make sense? So good. So this is good. That means we can even kick out this minus U2 factor. We don't need to worry about it that much. So that means all remain to do is to guarantee that we need. So this implies that our main task is to show that the set of small degree vertices expand by a factor of 2. And their intersection, when we do inclusion and exclusion, it's small, okay? This is the main thing we want to do. Okay. All right, so let's see how we're going to do that. Okay, let's see how we're going to do this too. First of all, let's focus on two expansion of, let's look at let's first look at the 2 expansion. For U1, the set of small vertices here, small degree vertices. As I mentioned, to have 2 expansion for just singleton, we need to remove vertices of degree at most 1, right? Those singleton, they even fail to expand by a factor of 2. So this is for sure we have to remove. We will include it in the set W to remove. Also, something like this, we don't want to see. This is the first kind, right? Second kind, you don't want to see in U1, 2 vertices, they share a neighbor. We want their neighborhood to be disjoint, not good, right? We want in U1, each guy goes out disjointly. This is good. Now, since we kick our vertices of degree at most 1, every one of this blob going out disjointly has size at least 2. We are kind of in good shape. We get 2 expansion, sort of, okay? So to avoid this scenario in the front from happening, then we will remove, then this is to motivate this, we remove path of length 2 with endpoints in S, because U1 is a subset of S, right? So you remove path with ends in the set of small degree vertices, okay? Right, this is the second kind of thing we want to remove to avoid this situation. Now, next, so this is for U1. Now we want to say, let's look at U2. We have to remove a little bit more. For the intersection, we want to control the intersection, remember? So let me draw a picture. We have U1. Here is NU1. We have U2. To control their intersection, note that if every vertex in U2 has at most one neighbor in N of U1, we're in good shape, right? So each guy sends at most one edge. You don't see this kind of thing, okay? Because if you see this, there's lots of overlap. If this is the case, this implies that we can guarantee that, then their intersection is at most the size of U2, because each guy in U2 sends at most one, right? So this also motivates us to want to delete not just path of length 2 based on small set of vertices, but also path of length 5 up to 5 based on the small set of vertices. But it could be that these two endpoints, they're identical. It could be a cycle even. So this might even be a cycle, or maybe this look like that. We don't know. So for this purpose, we motivate the definition. So we want to remove this is the third kind of thing we want to remove, like short cycles path based at S, right? We are almost done with this hand waving part. Right. This set is almost enough, the set of vertices we removed. There's one last part I want to mention. Vertex almost enough, but after removing the above vertices, okay, we remove a little bit. Let's say W prime, not yet W, okay? And we have our U1 and U2. We want to check their expansion. Now it could be that some U2 have too many neighbors, is too attached to W, to the set of vertices that we remove. It's possible, right? Which makes the vertices in U2, this vertex in particular, become small degree vertex. So we don't want to see this happening. We want to maintain them to have large degree. Okay? So then we need to further remove a small set B1, which in the proof, you can correspond that. For this, further remove So all the vertices removed up until step 3 is B0 in the formal proof. You can look at the correspond to the B0 in the formal proof. After B0, it could be that this is B0 here, kind of. Then some vertex sends too many edges. It becomes low degree. We don't want that. You further remove B1 to compensate that. And right. Okay, there are more things, but I don't want to get too. Let's get to the statement now. This is roughly the idea. Okay, we want to do some removal in an intuitive way. So the proof is a little bit technical, but if you look at this process, every step is kind of justified. So definition, this motivates the definition for 13. Take a set of vertices S. Okay, we will call an S ring is a path of length at most 4 with ends in S, or these two, or a cycle of length at most 4 intersecting S. Let me draw a picture. This is S. Either it looks something like path of length at most 4, so it could be like this, or a cycle of length at most 4 intersecting, something like that. This is definition, just I make it shorter so that it includes all this kind of configuration we want to remove. You see up here, we remove path of length 2 and up here in this corner. Okay. So now let's state lemma 414. We have some integer, not so small, 4 is enough. And we have a graph G, an n vertex graph with S being the set of small degree vertices. Okay, its degree is less than D. So capital D is say if you fall below capital D, you are small vertex, low degree. Suppose G has X vertices of degree at most 1, Y has at most and at most Y. Oh, I can just define it to be X, right? I don't need to say at most. For some X and Y, it has X, vertices of degree at most 1. Y is the number of S rings, okay? So as we do in the hand waving part, we want to remove this S ring. Then lemma 414 says, and furthermore, we have these 3 conditions. So now we should correspond these 3 conditions to the 3 pseudo-random property that I listed up here, these 3. The first one says that there are very few vertices of low degree, and they are pairwise far apart, typically. Okay, you have few vertices of degree at most 1, and you have few S ring. Then you don't have too many low degree vertices in distance 5 within each other, and not many S ring for some M. M is another parameter we set at the beginning. This is the first condition. Second condition is large set expansion for any A. As long as it reach size M, then its external neighborhood reach 80% of the vertices. Last one is no dense patch, upper uniformity. For any A of size, let's say at most 10m, not too large, then the number of edges induced on that subgraph, which I write E sub G of A, is at most dA over 100. Okay? So this means no dense patch, upper uniformity. Why? Because usually, let's take GMP. And P equal to some D over N, say, right? We take GMP, P is D over N. So that means the expected degree is D. So S is the low degree. Then expected number of edges on a set of size A is D times A over 2. So it's like 50. You are only 2% of what you expected. So this is, I'm saying something strange. But anyway, if you make the number correctly, this means that unlike every set, cannot be too dense. Okay, less than that. Probably we have to take these slightly, appropriately. So the conclusion is that we find a huge 2n over 5 expander implies that there exists W such that W is at most x plus 7y. So we want to bound x and y basically. And G minus W is 2n over 5 expander, what we want. Okay, this is the whole lemma. How much time I have left? Okay, 20 minutes. I think it will be enough to give the proof, 20 minutes. As I said, it's a little bit dry, but if you want to review it, you can compare the proof to the hand waving part up here, then things will become more transparent why every step is done that way. All right. So given these three conditions, how do we find large 2n over 5 expander? We're going to define B0. This is a formal proof. B0 is the set of vertices of degree at most 1 because they themselves do not expand by a factor of 2, and the vertices in S ring. So we will also remove S rings. Okay, these kind of things, we don't want them because they cause trouble. This is B0. And then immediately we can give a bound on B0 in terms of the parameter we set up. This implies that B0 is at most x, which is the vertices of degree at most 1, plus 5y. Y is the number of S ring, and each S ring has at most 5 vertices. It's either path of length 4 or cycle of length 4, right? And we also have that B0 out of the small set vertices is small. Again, path of length at most 4, so you only have 3 vertices sticking out of S with ends and in S. So there are y of them, this is at most 3y. Now this is B0. We define B1. This is the further set that we remove to make sure that after removing B0, vertices of large degree before do not become small degree, sort of. Okay? Is a subset, not a small set of vertices, or not B0 that we removed, B maximal set such that B1 is at most y, the number of S rings, and the edges induced on B0 union B1 minus S is large. So let me draw a tiny picture here. We have B0 as B1. So you see here, this means that it sends too many edges, right, to B0. So the number, this is lower, is quite large, at least B1 times some D over 2. It sends too many edges. So by removing B1, hopefully all the remaining vertices, they don't send too many vertices to B0. So all the remaining large vertex, they are still large vertex. Okay. In fact, I skipped one part at the hand waving part. I don't want to make it too complicated. We also set B2 to be MB1 intercept S. So B2 is here's the picture. This is B2 here. The picture might be a little bit misleading because B0 and S actually intercept, right? The B0 has vertices of degree at most 1, so it must contain something from S. But anyway, let me try this way. What's the purpose of B2? Let me first tell you that these 3 sets will be enough. Okay, so all that's remain is to prove that after removing these 3 sets, remaining graph expands by a fact, expansion of 2 for all sets up to size n over 5. But let me just kind of convince you what's the purpose of B2. The purpose of B2 is that we want to make, I wrote it here. What is it? We want to make NU1 disjoint from B1. What? So maybe we have to go up to the picture here. We have U1 and U2, right? U1 and U2. We want NU1, which is this guy here, to be disjoint from what? NU1 disjoint from B1. Ah, okay. You see what's going on? I see it. Because we want to, U1 is the set of small degree vertices. We want 2 expansion for them, right? So that's the sensitive set. We need to be careful. And since now we further remove B1, it could affect NU1. So we need to make sure that it's disjoint from, recall, our idea of making NU1 expand is to make sure that they don't overlap outside, and so they disjoint it. But if any part of this guy fall into the B1, the further set that we remove, we're again in trouble, right? So just after removing B1, we need to make sure that NU1 has nothing to do with B2, so that NU1 is disjoint from B1. Okay, we will see this later. I will recall this fact later. So now we need to show that W equal to the union of these suffices. Right. First, we're going to bound the size of W. First, we show that W is indeed at most x plus 7y, okay? Which is here. Where's the statement? Here, right? W is small and the remaining is expanded. Let's first prove that it's small. We know B0 is x plus 5y, right? So that means as B0, we just need to show that B2 is at most B1, which is at most y. Okay? Actually, B1 is at most Y is our choice, right? So we know B1 is at most Y. Why B2 is at most B1? This is because B1 can only have one neighbor in S, every vertex in B1. If it has two neighbor in S, this is a S ring, right? It should have been removed in B0. Okay, this is why. I'm not going to write it down. So B2, that means B2 is at most B1, which is at most Y by our choice of B1. So altogether, you add another 2Y there, done. So the difficult part, okay, which is also not too difficult to show the expansion. But actually for the expansion, we have to show there is a claim actually. The claim is that in fact, by our choice, B1 is strictly less than Y. It cannot reach Y, okay? We choose B1 is at most Y, but we can show that it cannot reach Y. Basically, the reason is that if we reach Y, then you can choose a set of size Y. Let me see. What's the reason? Let me write it down. Okay. Well, my note says, I think contradict to some maximality as B0 union B1 over minus S is at most 4Y. This is because B0 out of S is 3Y and B1 is at most Y, okay? And we have a bound on Y, which is M in the hypothesis of the lemma. So if B1 equal to Y, then this will imply that the number of edges induced on these is at least dy over 2. This is just by the choice of B1. Remember here, by choice of B1, we have this. But now B1 is Y, so I put Y here instead of B1, which since altogether they are at most 4Y. So this is at least D altogether over 8. But this contradicting to the upper uniformity. So you can never reach Y, in fact, a little bit smaller, one smaller. Now, next, we will, for shorthand, let's write H to be G minus W. We will show that H is a 2n over 5 expander. Okay. The idea basically is what I said before. So now I'm just writing down some details. So you take U, where U is a subset of H, of size n over 5. We need to show n in H its external neighborhood. The U is at least 2, right? 2U. So as we mentioned, we're gonna divide U into U1 and U2, okay? But before that, there's another claim, which is for n in V, not a small set of vertices, we have W, which is B0, B1, B2. And S, some part of S left over in H, subset of S. So here is H. If you take a vertex V now, out of S, out of W that we removed, it has large degree out of S. Okay, it has many neighbors here, basically, at least D over 4. The proof, I will not give the rigorous proof, basically by maximality of B1. Because if it sends too little neighbors out of S, it could have been added to B1, right? Added to B1 to maintain this two property. Because by previous claim, we know B1 is strictly less than Y. So we allow to add one more to maintain these. This is why I proved that it's strictly less. Okay? This is basically the reason. It's two-line proof, but let me skip it. This will be used later. What's next? Right, suppose another reduction we can do is that, how much time? Another reduction we can do is that we may assume U is not big. If U is big, bigger than M, we have large set expansion. For any set of size M, its external neighborhood is 80% of the vertices. Then it's easy. We take, here's U. If it's larger than M, we take a U prime, which is exactly M, and we know that its external neighborhood is huge. Okay? It's 4n over 5. So easily we satisfy what we want. Then formally, let me write it down. The external neighborhood of U is at least external neighborhood of U prime minus U, right? Which is at least, we look at the external neighborhood of U prime in G minus W, because we remove W to get H minus U. Then given the hypothesis, the first term is 4n over 5. The other term is small, which we assume in hypothesis. You can show that this is bigger than 2n over 5, which is bigger than 2u, because u is at most n over 5. We just need to prove, where is it? I wrote it here. U is the most, we want to prove 2n over 5 expander. So we choose a set U of size, right, n over 5 here. Okay. So this is also easy part. We're almost done. May assume. So that means we may assume U is small. Now we cut it up as we discussed. U is the small vertex and large vertex. U2 is a large degree vertex. Then we have our inclusion exclusion, but slightly different from the hand waving part because we further remove some sets. So the external neighborhood of U in H, we want to prove this is at least 2 of U, 2 times U. This equals 2. So this is the same as U1 union U2, right? Inclusion, exclusion. And minus their intersection. Okay. Well, here's another claim that NH2, there's no H2. Is at least 9U2, say. Okay. This is because I will just prove by picture. As I mentioned, U2, and you have U1 somewhere. U2 is not in S, disjoint from S, so it's a large degree vertex. That means U2 to its external neighborhood out of S must send lots of edges. This is the claim we have here. Every vertex not in S in H sends lots of edges outside of S, right? At least D over 4 by the claim. lots of edges. So that means this is dense. Not a good idea. That means lots of edges. Then upper uniformity implies that this must be large, because if it's small, lots of edges, too dense. That's the proof. Now, yes, and we also have these. Right? We have U2 sends at most one neighbor, because if you send two, this is in the neighborhood, that means you either have that or you have that. This is a S ring, a contradiction. We remove the S rings, right? So look at all these terms here. We have this term, last term at most U2, you minus another U2. Here you plus 9U2, so you're way above the 2U2 quota. All you need to check is that U1 expand by a fraction of 2, which is true, basically. You can check. I will leave it. Maybe if I write more, I will just confuse you. Since, let me just go back to this picture, right? The very beginning hand waving picture. Since we already removed things like this, so we don't have U1 neighbors meeting each other, they must go out. We also remove degree 1 vertex, okay? So almost a complete proof. I will end here and end today's lecture. It's a little bit technical today, but next time we will see its application of finding almost optimal bound on long cycles in random graph and Hamiltonicity threshold. Okay, let me just stop the whole thing at the informal statement. I think the formal statement is not that illuminating. So this is what we did today, the informal 4.14. Any questions?
I have one question. So, then how you can show that pseudo random have the condition, satisfy the condition of the power lemma? So is it easy? Or?
Yes, I think that's quite standard to check. I will show it next week, just quickly. Well, rather, I will show you the statement and I will leave it as exercise. Basically, through some sort of Chernoff or Azuma-Hofting inequality concentration, or first moment, second moment. So if you check the along Spencer first two chapter on first moment, second moment, you just check the expectation, use either Markov or Chernoff or Chebyshev, they are enough.
You said pseudo random, right? Yes.
Hmm? For example, the large set expansion, it was an exercise before, so we know it already, right? No dense patch, you say, okay, what if there's a small patch that's dense? You calculate the probability, it decay exponentially, use some concentration turn off, I don't know, something like that. Then you take a union bound over all possible small patch, and that's the whole proof without the calculation. Yeah. And the small degree vertices also linearity of something like that, I think. Oh yeah, for the small degree vertices and they are pairwise far apart, you can just calculate the expecting number of paths whose endpoints have small degree, right? If you calculate the expectation, then you use the second moment to show that, or first moment to show that. Unlikely you will have such short path or short cycle with endpoints or with one of its vertex having low degree. Did I show it in my notes? I think I leave it as exercise. Yes. Yeah, if you have trouble showing it, you can go to Kim Jae-hong 교수님.
Any other questions? If not, I mean, we can end today's lecture, and next one is, I mean, next Monday. We will resume on the same time on next Monday. Yeah.
Yeah, okay. Thanks for coming today.
Thank
See
you for
guys next week.
the lecture.
Great.